okay? So that's finding moles of A. You are going to use the mole ratio. Where do we get the mole ratio from? Nope. From the balanced equation, from the coefficients in the balanced equation. And now you have found moles of B. The last step for this one is to find the concentration of B. Now you cannot find concentration by dividing. Do you remember how to find concentration? We had a formula for that. What is concentration? How would I say, let's say I wanted to find concentration of B. How would I write that down? Concentration of B. What notation would I use? I would use square brackets. Use square brackets. My concentration of B, what is concentration measured in? Moles of B over liters of B. Guess what you have just found? You found moles of B. Yes? The liters of B will be given in the question. Okay? So you can't convert. You're not going to go times line. You're just going to divide. Okay? So let's take a look at this question here. We have, what kind of a reaction is this? Tell your partner, what type of reaction is this? What type of compound is H2SO4? It is an acid. What type of compound is NaOH? A base. And what did we get when we made that? When we reacted them together, we got water and a salt. Okay? Now, our only coefficient here is a 2. So everything else, oh, there's a 2 here as well. Now, one thing you need to look for is we've got a whole bunch of numbers here, right? 15.6 milliliters of 0.200 molar H2SO4. So we know 2 things about the H2SO4. Not just one thing, we know 2 things. Do you remember what of means? Of means multiply. So you are going to multiply 15.6 milliliters times 0.200 molar. But before you do that, what should you do with your milliliters? you should convert it into liters. So we're going to say, okay, my 15.6 milliliters is equal to, how many liters is that equal to? How can you do this conversion quickly? You need to move your decimal place. How many places? 3 places. 1, 2, 3. So my decimal is going to go here. I've got the 5 and the 1. What do I do here? I put a 0. And so that's going to become 0.0156 liters. What should I be doing with the capital M, molar? I should write it as moles per liter. So I'm going to say I have 0.200 moles per liter. Now, I've already done this down below, so I'm not quite sure why I'm doing it again. It does say calculate the concentration of NaOH, so my unknown is my concentration of NaOH. I have moles per liter, and that is of H2SO4 per liter. And remember, you're going to be using molarity as a conversion factor. So we are going to start with, since it's a conversion factor, then the other thing that has to be the initial quantity is the 15.6 milliliters of H2SO4. That's our initial quantity. So we are going to start with milliliters of H2SO4. We're going to convert to moles of H2SO4. What do we use to convert between milliliters? Or sorry, let's make that liters because we've already changed it. What do we use to convert between liters of solution and moles? Concentration, so that's going to be our moles per liter. So we will use that. And then once we have moles, step number 1 is finding moles of A. What's step number 2? Finding moles of B. What's B in this case? We want to calculate the concentration of NaOH. So we want to find moles of NaOH. And finally, we want to find the concentration of NaOH. Okay, let me just grab the numbers here. We have 0.2 moles per liter. Concentration of H2SO4 is 0.200 moles per liter. The volume of H2SO4, woo, that's a weird S, SO4 is 15.6. And we know that the volume of NaOH is 25 milliliters. We have a 25 milliliter sample of the NaOH. Now, if you're reading this question and you're like, there's a lot of numbers, and I don't know which is going to be my initial and which is going to be my unknown, you can always write them out like this. Okay? Your unknown is always going to be the one that you obviously don't know. What is the, calculate the, find the? That part's easy, right? So you know you're not going to be starting with 25 milliliters because that is part of your unknown. Yeah? NaOH is unknown, so volume of NaOH is going to help me calculate my unknown, but it's not going to be where I start from. I have 2 quantities for the H2SO4. One of them has moles over liters, so that has to be the conversion factor, which makes this my initial quantity. To be fair, if you were to write the conversion factor and then multiply it by the initial quantity, that would work out exactly the same as if you write the initial amount and then multiply by the conversion factor, because 2 times 3 is equal to 3 times 2, okay? So you can't really go wrong. And this was 0.0156 liters. So we want to find, let's see, I want to find moles of H or NaOH. We are starting with 0.0156 liters. And we have, and this is of the H2SO4, we have 0.200 moles of H2SO4 per liter. Is it important that I write the H2SO4 here and here? Yes, because we're transferring, we're converting between different substances. So you need to know which one you're talking about each step of the way. Okay. And then we need to cancel moles of H2SO4 and find moles of NaOH. Where do we get those numbers from? They aren't given up here. Those are from our balanced equation. So we go back here and we say in front of the NaOH there is a 2, and in front of the H2SO4 there is a 1. So there are 2 NaOHs for every 1 H2SO4. This is from the balanced equation. And we get 0.0156 times 0.2 times 2 equals 6.24 times 10 to the negative 3 moles of NaOH. But that's not what the question asked me for. The question asked me for the concentration of NaOH. How do I write concentration of NaOH? Square brackets. Concentration of NaOH equals, what's the formula? Moles over liters. So we're going to take the moles of NaOH, 6.24 times 10 to the negative 3 moles of NaOH, divided by which volume am I going to use? I have 2 different volumes. I have 25, whoa, what's that color? I don't like that color. That's too bright. Too bright? No. Just erase the color. Oh well. Maybe I'll just live with it. Okay, that's fine. 25.0 milliliters, and I also have 15.6 milliliters. Which one am I going to use? The 25, because it is to do with the NaOH, and I am finding NaOH. Now, what do I need to do with that 25 milliliters? Convert it to liters. So instead of 25 milliliters, I'm going to move my decimal place 1, 2, 3 places. So it's going to be 0.0250 liters. So 0.0250 liters. Do that calculation. Divide by 0.025 equals 0.2496 moles per liter, and that's moles of NaOH. Whoa, where'd you go? There we are. Now, sig figs. There seem to be a lot of 3 sig figs there. Yeah, it does seem to be 3 sig figs. So how would we write that as 3 sig figs? 0.250. And I could, if I wanted to, write moles per liter. Or I could, if I wanted to, write molar. Then I would box my final answer. Can I show you something that people do that often they get wrong? Okay, I'll show you a mistake here. So I'm going to focus in on this line here. Maybe I'll write this in red so you can see what's happening here. So people will do this and they'll get 6.24 times 10 to the negative 3 moles. And then they'll say, well, I want moles per liter. So why don't I just throw my liters down here? Why is this wrong? It looks like what I did here. Why is it wrong to do it here? Well, what if I did this? What if I said 1 times 2 times 3 equals 6 divided by 4? Is that okay? No. So why would it be okay that 0.0156 times 0.2 times 2, which is equal to 6.24 times 10 to the minus 3, it does not equal 6.24 times 10 to the minus 3, divided by 0.0250. This number here, what color do I want? Let's grab some green. This number here is equal to this times this times this, divided by 1. It is not equal to 6.24 times 10 to the minus 3 divided by 0.0250. If you do that division, it's like saying, oh, I've multiplied these three things together and they are equal, and now I'm going to just divide by 4 and say it's still equal. You can't do that, because that would be like saying 1 times 2 times 3 is equal to 6. Now I would like to divide 6 by 4, so I'm going to just put my divide by 4 here. You can't do that. If you want to now, in a separate step, go 6 divided by 4, and you get, 3 halves, which is 1.5, then you could do that, but you cannot put it in the same line. Does that make sense? Okay. So you must do the division on a separate line. Or, what if you want to do it all in one line? Make it neat. No, I'll show you. I'll show you what we do if we want to do it all in one line. We would have, we want to find the concentration of NaOH, which is equal to the moles over the liters. And we started with 0.156 liters times 0.200 moles of H2SO4 per liter times 2 moles of NaOH for 1 mole of H2SO4. So far I'm good, right? But I've said I'm solving for moles over liters. So if I want to do that, I can just do this if I want to. I can put a 1 in the numerator, and I can put my 0.0250 liters in the basement. I can do that. You're allowed to do that. If that makes you uncomfortable, do it on a separate line. like here. Okay. We are going to, sometime this week, probably Thursday, do a titration. It's fun. A titration is fun. It is a lab technique. I have substance A and I know its concentration. I have substance B and I don't know its concentration, but I know that A and B react together. Yes? Okay. So there's a few words that you need to know about this. We have a standard solution. Standard just means known. You might want to write that down. Standard means known. Not just any old known, it means it's a known concentration. Your sample solution, can you guess what that one is? That is your unknown concentration. It's the one you want to find out. Do you remember what a burette is? Is that long, tall in the back there? Yes? Okay, that's a burette. And it has the stopcock on the bottom. I'm sorry for that term. That's just what it's called. Okay? And it shows you the amount of water that has been dripped out. You measure a starting volume, VI. You measure a final volume, VF. And then the V that is delivered is equal to VF minus VI. Does that sound familiar? Yes, okay. Did you do anything with acid-base indicators last year in grade 10? Little bit? Okay, so an acid-base indicator is something that changes color depending on the concentration of the acid or the concentration of a base. And we are going to be using the most common. Could one of you guys close the door, please? There's like, I don't know what's happening in the hallway. Thank you, Ravina. The most common indicator that we will use is called phenolphthalein. And yes, you have to spell that correctly. No, I'm just kidding. No, you don't. Okay. It's called phenolphthalein, which I think is pretty awesome. It sounds like something Sylvester the Pretty Cat would say. Okay, phenolphthalein. But it is pink in acid, or no, sorry, it is colorless in acid. And it is pink in base. And that's what we call an indicator. It indicates whether a solution is acidic or whether it is basic. At some point in a titration, we are going to reach the equivalence point. The equivalence point is when A and B have completely reacted. Okay, so you've got some A and it needs to react. Let's just say that A are these pens. Okay, let's say that A are these 3 pens. And let's say reactant B is the pen caps. Yes? So I add a little bit of the pen caps to the pens. Have I reached the equivalence point? No. I add a little bit more of the caps to the pens. Have I reached the equivalence point? No. I add a little bit more. Have I reached the equivalence point? Yes, I have. Now let's make this even better. Let's say that this is these guys are my acids. Okay, acid. And these pen caps are my base. Yes? So right now, in my solution, can you imagine a bucket here with these pens in it? Yes. Okay, so we have a bucket with pens in it, and I have 3 molecules of acid. What color is phenolphthalein going to be? We're in acid, 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 acid. It's colorless. So now I'm going to add some base. And I have made water. Okay, I added some base and I made water. Okay, so this now with the pen and the cap together, that's water. So I have water. What do I still have left? 2 acids, right? What color is phenolphthalein? Acid, acid, phenolphthalein is colorless. I add a little bit more. What was this? This is the base. I add a little bit more base. What did I just make? Water. I just made more water. So now I have 2 waters and I have 1 acid. Okay. What color is phenolphthalein? Colorless. I add 1 more base. And what do I have now? I have 3 waters. And phenolphthalein actually at pH 7, which is neutral, is still colorless. And now I add 1 more base. What color is phenolphthalein now? It's now turned pink. This point here, where I added 3 bases to my 3 acids, that was the equivalence point. This is the equivalence point. And if I add 1 more drop of base, I've gone a tiny bit past the equivalence point, but it turns out it doesn't actually matter in terms of like the volume I'm measuring. It's so small, it doesn't make a difference. But if I add 1 more drop of base, then my indicator changes color. Okay? What point is it where they're all like this? That is our equivalence point. 1 more drop later and we hit the end point, which is the point at which the indicator changes color. But it only takes like 1 drop to do that. So we just kind of ignore that drop and say close enough. Okay? Because there's going to be more than 3, right? You're going to be adding like a lot. Okay? So 1 more drop and then you'll get to your end point, which, what is the end point? The end point is where the indicator changes color. What's the equivalence point? It's when all of your acid has reacted with all of the base perfectly. Is there any extra acid? Is there any extra base? No. That's our equivalence point, is when you have perfectly reacted the exact amounts with each other. That is your equivalence point. The end point, as we just said, is where the indicator changes color. It should match up nicely with the equivalence point. They should be within about a drop of each other, okay? Now, with any really well done lab, you're not going to just do a lab once because your results might be sort of iffy, yes? But if you repeat the lab more than once, then you're going to get an average, and an average is probably better. You're getting better data. And if you do it 3 or 4 times, your data is going to get better and better and better, right? Because you're coming closer to an average. So if 1 point is too high and 1 trial is too low, they'll average each other out. So when you're going to do your titration, you are going to do it, and hopefully you won't have any outliers. An outlier is in a titration is a value that does not agree within 0.2 milliliters. Okay, that 0.2, that's a fairly arbitrary value. It means I sort of picked it out of the air. I could have chosen 0.1 milliliters, but this is your first time titrating, and if you can get within 0.2 milliliters, you're doing pretty well. Okay. So here's what we're going to do. Here's a picture. Tomorrow I'll actually do a demonstration for you. Okay. When you're finished your quiz, we'll do a little demonstration. Here is our burette. And in the burette goes the standard solution. Is the standard the one you know or the one you don't know? This is our known. Okay. It's also known as the titrant, but I'm not going to get that excited about this for this year. Okay. All right. What's this doodad called? That piece of equipment there. Erlenmeyer flask. Remember, it's the one that has all the E's in it. Every single vowel is an E. Erlenmeyer flask. And in our Erlenmeyer flask goes the sample solution, which is also the unknown. You can call it the analate, but you don't have to, okay? So I'm going to put those in black diamonds. Analate and titrant. We'll just call those black diamonds. If you want to learn them, you can, but you don't have to, okay? And of course, down here we have the stopcock that lets the solution drip in or not in, just out. We can't drip stuff in. That doesn't make any sense. All right. And also into the Erlenmeyer flask, we will not only put the sample, but we will also put the indicator. So what we'll do is we'll have a flask and it will have some acid in it, and we'll put in some phenolphthalein, and the phenolphthalein is colorless in acid, so it will be colorless. You'll be like, wow, that was really boring, nothing's happening. And then from the burette, you will drip in and you will swirl your flask as it drips in, and it will, oh, you'll start to see pink because you're adding base. All right, and eventually you'll get to a point like that you'll see pink and then it'll disappear. You'll swirl it and it'll disappear. You'll see pink and it'll disappear. Eventually the pink color will stay, and you'll be like, oh, I have reached the equivalence point. When you see the pink color, you have reached the equivalence point. You're going to repeat this until at least 3 volumes are within 0.2 milliliters. So that means you're doing at least 3 trials, maybe 4 or 5. Of course, if you do 3 trials and we're out of time, then you're like, okay, I'm out of time. Too bad. Okay. Eventually, you are going to take an average and you will exclude any volumes that are not within 0.2. And then we just do stoichiometry with it. We just do those calculations that we just did, which means you're going to find moles of your known. You're going to find moles of the unknown. And then you're going to find concentration of the unknown by taking the moles of the unknown divided by the liters of the unknown. Okay? I know, right? All right, so here we go. Here's like a little picture thing. Like I said, we'll do an actual one tomorrow so you can see it physically. 10 milliliters of HCl is titrated with 0.9973 molar NaOH, according to the procedure shown. So here we have information about HCl. We know its volume, we do not know its concentration. Is HCl the known substance or the unknown substance? It's the unknown, because it's the one with the question mark. So what do? In our beaker, we have some HCl. And you want to measure 10 milliliters really precisely. Do you guys remember what piece of equipment we can use to measure a volume very, very precisely? We could use a burette, but we're going to be using the burette for the titration, so we are going to use a pipette. And because we want 10 milliliters, it's going to be a 10 milliliter pipette. Yes? So we suck up the HCl into the pipette, and then we take the pipette over to the flask and we drip out the acid into the flask. Okay? Next, we're going to have our burette. Okay, and we're going to fill it with the sodium hydroxide solution, and we know that the sodium hydroxide is 0.9973 molar sodium hydroxide. This is our known substance because we know its concentration. If you remember, on our burette, we read and we say, oh, how much does it start at? Up at the tippy top, there is a 0, and down at the very bottom, there is a 50. So if it says 3.11, remember burettes read which direction? Burettes read down. So we are starting at 3.11 milliliters. That's what it says when you read downward. All right. We take our flask, our Erlenmeyer flask. Remember that this is the HCl. That's our unknown, UNC. And we put in some phenolphthalein indicator. And then we start dripping out the sodium hydroxide, right? So we drip in the sodium hydroxide until the indicator changes color. And our final volume here is 15.82 milliliters. And look, we got a permanent pale pink color. I'm sorry, it all looks like gray on your paper. Okay. We will calculate, we know our initial volume, we know our final volume for the NaOH. So we can calculate the volume of the NaOH. It's the final minus the initial. So we finished at 15.82 milliliters. We started at 3.11 milliliters, so there was 12.71 milliliters of NaOH delivered. We know that the concentration of the NaOH was 0.9973 molar. I'm going to take all of this data and summarize it. Down here we have concentration of NaOH equals 0.9973. I don't want to write it as moles. Molar, what do I want to write it as? Moles per liter. Do I know anything else about the NaOH? I know the volume of the NaOH. So I also know that the volume of the NaOH is 12.71 milliliters. How many liters is that? Is it 0.12 or is it 0.012? 0.012, and then of course we have the 7.1. Can't forget about that. But so that's what we know about the NaOH. What do we know about the HCl? Let's go back and take a look. Do I know the concentration of the HCl? No, that's my unknown. But what do I know about the HCl? I know I measured out 10 milliliters, right? This was 10 milliliters of HCl. So I know that I have the volume of the HCl is 10 milliliters, and I know that the concentration of the HCl is what I do not know. Out of these four things, which one am I going to use as my initial quantity? Out of these four things, which one am I going to use as my initial quantity? Is it going to be 10 milliliters of HCl? Is it going to be 0.0171 liters of the NaOH? Or is it going to be the concentration of the NaOH? Which one is my initial? NaOH is my initial because this is my unknown, right? So I'm going to say this is my initial quantity. The moles per liter is going to be a conversion factor, and I'm somehow going to have to use this to find the concentration. Is good? Okay. So let's take a look what we've got here. We're going to start with our 0.1217 liters of NaOH, convert that to moles of your known, and then convert it to moles of your unknown, which is the HCl. And then finally, in a separate step, you're going to find the concentration of HCl. So, liters of NaOH times moles per liter of NaOH. Use the balanced equation to find 1 mole of HCl for every 1 mole of NaOH. Where's our balanced equation here? It is up here. Look, everything's 1 to 1 to 1 to 1. Super easy, yeah? So that's nice. Not everything's super easy, but at least that conversion is. We do that and we get 0.01267 moles of HCl. Would it be okay at this point, because I want concentration of HCl, to divide by my 0.0100 liters? Is that good or is that bad? That's bad because this calculation is equal to that number. It's not equal to that number divided by 0.01. Okay, so we have to do that on a separate line, all by itself. Concentration is the moles over the liters. And we know because we measured out 10 milliliters of the HCl, and that's what we got. So, for the rest of class, could you please try some of these questions? What? No, just no test. Quiz will be on Friday. No, Thursday we're going to do a lab.